All right, well, it's my pleasure to introduce Lucas Ruhstorfer from the TU Kaiserslautern, and today he'll be speaking on Jordan decomposition for the Alperin-McKay conjecture.
Well, thank you very much, Jay, and also I would like to thank the organizers for inviting me and also for the opportunity to give a talk here. And what I'm going to talk about is, well, something I've completed by now, but which has also now some implications for what I'm doing now. And since I know that not all of you are too familiar with modular representation for finite groups, I'll just try to make the first part of my talk at least somehow an introduction in these local global conjectures. So I guess I have to not convince anyone in this room that a good story always starts with the group G. And for me, G is always a finite group. And I would also like to fix a prime number. And to make things interesting, I assume that my prime number divides the order of my group. Okay, so what people do in this business of modular representation theory, they look at what's called an L-modular system. And since I'm not really interested in whether representations can be, or for which fields representations can be realized, I will always assume that this is large enough for the group to take into consideration. And just to remind you what this triple actually means, so first of all, capital K in my talk will be a finite field extension of QL, the L-adic numbers, and O will be its ring of integers. And since this is a finite field extension of QL, so you're looking at a local field, so this will have a unique maximal ideal. So we can talk about spoken field over the Jacobs radical of O, and this will be a field of characteristic. Right. So once you have this set up, you can consider your group algebra over your field O, or over your ring O, and you can decompose this group algebra into indecomposable GG bimodules, or if you like, indecomposable ideals. This gives you what is called the decomposition into L blocks. And somehow, the nice thing about this ring O is that it actually sits between your field capital K and also your field little k. So kind of the philosophy is that O gives you information about both capital K, field of characteristic 0, and little k, which is a field of positive characteristic. Right. So the first thing you observe, if you tensor this group algebra with capital K, you also get a decomposition of your group algebra. And therefore, if you look at the irreducible modules of G over this field capital K, you get a partition of your modules into these blocks. Need an O here. Right. So this is the first thing why actually this modular representation theory is so interesting, because you want to know somehow information about modules and characteristic 0, but somehow you can relate them to this L-modular structure of your group algebra. And Brouwer then observed that to each L block you can associate two interesting invariants. Namely, first of all, you can associate the defect group T, it's just an L group, which is uniquely determined upon conjugation in the group G, and also you get an L block. So let's say this block is called capital B. Get an L block little b of the normalizer of your defect group, and this guy is also defect group, and it will be the same defect group as your block capital B. Okay, so this guy is called the Brouwer corresponding of B. And what many people then observed is somehow that the representation theory of your original block capital B should be somehow similar to the representation theory of its Brouwer correspondent. And there's some really precise conjectures and I would like to start with a conjecture by Rouhstorfer, which tells you that if the defect group D is abelian, then your blocks and the module categories of the blocks should be derived equivalent. Okay, so this is kind of a very structural explanation why the representation theory of these blocks should somehow be related. But if you have such a derived equivalence, you could of course also look at the implications on the level of characters. And this is somehow what the Alperin-McKay conjecture does. So this is now for general defect group. Oh boy. General D. This conjecture claims that you have a bijection between the height 0 characters of your block B to height 0 characters of the Brouwer correspondent. Now just say briefly what the height 0 characters are. So recall oops. So height 0 characters are all the characters in the block such that the L part of the degree equals the L part of the degree of the defect group in the group G. So if you have a block whose defect group is just a pseudo-P subgroup, you precisely get here the characters whose degree is not divisible by L. So in some sense, for maximal defect, you get a refinement of the McKay conjecture, which tells you something about L-prime characters. Right. So in the case that your defect group is abelian, Rouhstorfer's conjecture will actually directly tell you that the Alperin-McKay conjecture is true, but this is a bit more general and says something about general defect group. Okay, so So in the remainder of my talk, I will just focus on the Alperin-McKay conjecture, because this is, well, it's kind of more difficult to really construct a derived equivalence between two blocks, but somehow it's a bit easier to just count characters, right? So, and also the other advantage is that we have actually a reduction theorem of the Alperin-McKay conjecture to simple groups. This is theorem to Britain. Which tells you that the AM conjecture holds for all finite groups if the so-called inductive AM condition, which I will just abbreviate as IAM, holds for all finite simple groups. Okay, so the kind of nice thing is that this is somehow a reduction to really simple groups, and we know that simple groups are classified by now, so we just have to deal with a few families of simple groups. So we're almost done, right? But unfortunately, these inductive conditions, they are really difficult to check, because they're just not telling you that you should try to prove the conjecture for simple groups, but they tell you much more, or you need to prove much more. And just to give you an idea what they actually mean without actually saying or writing down any definition, because they're way too convoluted to state in a talk, at least that's my opinion. I will just give you an idea of what is essential here. So take your favorite finite simple group, and then we let G be its universal covering group. And then IM holds for a block B of G So I will just leave some blank space here. So what you of course want is at least this bijection, right? So, and now if you're kind of in a situation, you look at a simple group, it's universal covering group, and now you want to build up inductively representations, you need to say something about automorphisms acting on your representation. So this bijection should also be equivariant with respect to the action of automorphisms, which stabilize your block and your defect. I want this to be equivariant. And also, you need to say something about what happens to your actual representations, because you somehow want to go to overgroups, and now you're wondering what happens with the representation here and the representation there. And this is kind of the subject of Clifford theory, which should be preserved under this bijection. This should also be preserving the Clifford theory. With respect to G being a normal subgroup. Oops, that's not space. Difficult question. Yes. With respect to G, D. Right. No problem at all. So this is kind of really the tricky part, I would say, that you have to say something really about the Clifford theory. And there are also some, let's say, more, I mean, the real conditions are not that easy to state, so they're really technical. They usually go over a page or so. So I don't want to say what is really going on there, but you really have to say what happens to your representations if you go to certain overgroups, and what happens to your blocks if you go to overgroups. So it's really quite involved. Okay, so let me just say, so in particular, so what do I mean by Clifford theory in this sense? So extendability is preserved. So if you take character chi and this character, if you assume that this character extends to some overgroup X, where let's G. X is a subgroup. Automorphism group. This should happen if and only if its correspondent omega chi extends to the corresponding non-local subgroup. So NGB. And you would also like to say something about characters which do not extend, which just give you a co-cycle because they're invariant, and also this competition tells you in particular that the co-cycle should be preserved. So more generally, the co-cycle H2 and I guess a lot of people would just hope that you can really write something like that down in general, but this is really not sufficient because you really need to say something about representations, because you can, if you have an invariant representation, you have different projective representations associated to it, and also because you need to somehow worry about what happens on the center of your group. you have to also say something really about the actual representations, not only about the cocycles. And that's what makes this condition a bit, difficult to say, because you actually have to do actual computations with representations, not only computing cocycles. Okay. Right. So this is somehow an idea what all these inductive conditions mean. And as we learned before, is that most finite simple groups are groups of Lie type. So if we really want to understand this condition for simple groups, we should look at the representation theory of groups of Lie type. Okay. So from now on, my G will no longer be a finite group, it will actually be what is called a connected reductive group, which is supposed to be defined over an algebraic closure of Fp. And we're interested in cross-characteristic representations. So we assume that our P is different from L. And furthermore, we assume that we're given the Frobenius endomorphism, which defines some FQ structure for some Q power of P. And this, and if you take then the fixed points of G under this Frobenius endomorphism, we get a finite group GF. And we are now interested in understanding the representation theory of that finite group. So if you've never seen this setup before, just think of G as GLN or SLN, then your F could just be the map which sends every matrix entry to its qth power, say. And then if you take fixed points, you just get GLN over FQ.
Is there a particular reason why you focus on cross-characteristics?
Yeah, because the defining characteristic case is essentially done.
Okay. So is it easy or?
It is not easy in the way that it requires really some work to verify it. But if you are in the defining characteristic case, your blocks either have trivial defect or a Euler subgroup defect. And in this case, you're essentially in the case of the McKay conjecture. So what you need to do essentially for the Alperin-McKay conjecture is you need to solve the McKay conjecture, and then you automatically more or less get the Alperin-McKay condition. So this is why I will not say something about the defining characteristic case. But here it's much more involved, and the block structure is really difficult. And but at least we have some way of parametrizing blocks. And this is done as follows. So what you do is, and this is quite a standard construction in this business. So you take a group which is dual to your original group. So which means, so somehow what that means is you have your group G. This group has a root datum, and what you do is you basically swap the roles of roots, co-roots, and then you get another reductive group. And this is just a dual group. And then you take somehow a Frobenius endomorphisms, which acts in the same way as F on the identification of roots with co-roots. That's essentially what you do. And this is just possible. And so what you can do is, so why are you interested in these dual groups? Because for every semi-simple element of your dual group of L prime order you can actually associate a central idempotent in your group algebra. And of course, once you have a central idempotent, you can look at your group algebra times the central idempotent. This will give you a direct summand of the group algebra you started with. And unfortunately, these idempotents will not be primitive, so they don't give you blocks, but they give you at least some approximation to it, namely some of blocks. But you, in general, don't know how many blocks you get. Okay. And there's this theorem by Michel, which tells you that you actually get a decomposition of your group algebra. And you just run over all conjugacy classes of the dual group.
Semi-simple conjugate classes.
Yeah, I was tempted to write them, but actually Alperin order would also imply something. But I can't. Elements of semi-simple. Yes. Because they're Alperin.
Oh, the element has L prime order.
Oh yeah, right. Yeah, so I should really write it. Yes. Yeah, so this is kind of the same thing as what actually goes on in the ordinary representation theory. You just get this partition into Lustig series, and here you just take all elements of L prime order instead, and you get a decomposition of your group algebra in these different sums of blocks. And somehow the philosophy is now that instead of trying to understand all representation at once, you just try to tackle each of these individual S's at one time. So this is going to be our next aim. So understand the red theory. Fixed. Right. So I think so this leads us actually to our next theorem, which is like very, very useful in this whole business. Which is due to Bonnafé-Dat-Rouquier. And this tells you something about such a fixed series S. So what you can do is you let L star be the minimal Levy subgroup of G star such that the whole centralizer is contained in this Levy subgroup. We want to make this Levy large enough so that it contains the whole centralizer. So, and then somehow a Levy subgroup is again just given by its root datum. So what you can do is you can associate again by duality a Levy subgroup of your original group L to it. So, and then the theorem is following, you get a Morita equivalence between the original sums of block you started with and the corresponding blocks of your Levy subgroup. Okay, so and yeah, this is, if you know some theory, this is really given by the Lustig induction. And yeah, and what the nice thing is, you can really see that it's kind of a reduction theorem, because you start with your group G, you want to say something about the semisimple, the characters in the semisimple element S, and then you go down to your Levy subgroup L, which will also be connected reductive, but usually smaller. And just to give you really an example of how this theorem could be applied, so say your group G is GLN, then also your dual group will be GLN as well. And well, you just consider a semisimple element S. The semisimple element just means diagonalizable, so I can just take an element which is already a diagonal matrix with eigenvalues number 1 up to number n. And I just assume that each of these eigenvalues are pairwise different, which means if you've done a linear algebra course, you can compute the centralizer of the semisimple element. This will just give you a torus, so the diagonal torus, as a centralizer of S. And this is the torus. Diagonal matrices. So now we can apply our theorem. Now we actually see this guy here, this Morita equivalent, this original thing. Yeah, and just try to understand something very complicated about blocks in GLN, and you see, okay, it's equivalent to just an abelian or characters of an abelian group, a modular category of an abelian group, and we know everything about abelian groups. So this gives you a really complete description of your block here in terms of something of an abelian group. Okay. So of course the situation is not always that nice, because there was this condition that your Levy subgroup has to contain the full centralizer of S, which means that it could potentially happen that there is actually no Levy subgroup which contains the full centralizer, but is different from the group you started with. So you can't actually go down any further. And this is what people call a quasi-isolated block, namely block B of this is called quasi-isolated if the centralizer is not contained in any proper Levy subgroup of G star. Okay, so no matter what you do actually, you always end up with these quasi-isolated blocks. And you have to, even if you apply this theorem by Bonnafé-Dat-Rouquier, if you're not done yet, you have to still say something about the representation theory of these quasi-isolated blocks. Okay, so we have a beautiful reduction theorem to these quasi-isolated blocks. So it's, of course, quite natural to try to apply this to our Alperin-McKay conjecture. Okay, so first of all, we are just interested in simple groups, so we don't really need the whole apparatus of connected reductive groups. So my algebraic group G is now only simply connected, and such that the model of the center of my finite group, this is supposed to be a non-abelian simple group. And we assume that GF is its universal complement. Now, this time we don't think about GLN, we think about SLN. SLN has a center, just the diagonal matrices. If I want a center, you would usually get a non-abelian simple group. Unless you're very, very small, then you might get just a solvable group, which we don't really care about. And also, GF will usually be its universal covering group, unless you have an exceptional Schur multiplier, which is also very few cases which are not so important if you look at the grand scheme of things. Okay. So, and the first thing, if you really want to apply this reduction theorem, is you have to actually find a way of making this whole thing compatible with automorphisms. And this is not so easy at all, because it's first of all not so clear what type of automorphisms you get when you try to apply this to your Levy subgroup, because it can be somehow embedded weirdly in your group G. So you also need to somehow keep track of what you're doing. So it's really important to first of all find a good way of constructing automorphisms. So the first thing you can do is you find such a nice systemize a Boolean subgroup. Let's call it A. In your automorphism group, such that the image of this group, together with the diagonal automorphisms, in your automorphism group is precisely the stabilizer in the automorphism group of L and your idempower. So the point is, so you have your group A. This essentially consists of field and graph automorphisms your group has, and then you also get diagonal automorphisms. Those are the ones, for instance, if you look at SLN, those are ones given by conjugation of elements of GLN. So you these are kind of quite easy when you consider this equivalence. And then you construct somehow this group A such that it actually gives you the stabilizer in the automorphism group of L and your I. So you somehow have to change a little bit your automorphisms. Okay. And the first thing is, if L does not divide all of A, then you can actually just add A to your Morita equivalence. You get a Morita equivalence again. This guy will be Morita equivalent. I mean, that looks quite harmless, but it's actually not so easy to prove because you have to think add on top automorphisms of your group. You cannot really expect in general that your Morita equivalence just lifts. The point here is that you know by this recent work of Bonnafé-Dat-Rouquier, at least that this Morita equivalence does not depend on the choice of your parabolic subgroup, so you can at least get some handle on cyclic A in a way, but in general A will not be cyclic, so you have to really do something here to lift this equivalence.
I've lost track. Which levy is L at the moment?
The L levy is the one in the theorem here.
But it's
So
all refers back
but we're
to-
not just looking at these quasi-isolated things now. We're
No,
back to all
because
true
then you couldn't do anything. Sorry.
No, I was confused because
Yeah.
I thought it was. Is that right? Thank you.
Sorry, if I didn't make that clear. So the point is really you have this theorem and you would like to apply it, but there's of course like all these technical conditions you somehow need to transfer. And one of the most important conditions is that if you take character, you want to extend it somehow here, does the corresponding character extend here? And this is somehow what I was doing here, but this is so you can exactly see that if a character extends here to its inertia group, then also the corresponding character will also extend. And this is kind of the key result if you want to reduce these conditions to really quasi-isolated blocks. So you start with your block of G here, and then you try to pass all these conditions to your Levy subgroup L. You'll get some different conditions because your Levy subgroup is not a simple group anymore. And then you go by using group theory, theoretic arguments to the commutator subgroup of L, which will be a direct product of simple groups. And then you assume inductively that you know everything about quasi-isolated blocks, and then you use this to really reduce to quasi-isolated blocks with simple groups. And this is kind of the second theorem. And so I would just like to leave one line blank here, which I would at some point really like to erase from my theorem. But let me just state the theorem how it's supposed to be. So if every quasi-isolated block, so block means a block of a simple group V type, some characteristic P not equal to L, satisfies these inductive conditions, then the inductive conditions also hold for the group you've started with. Which means that you essentially just have to look at quasi-isolated blocks. And there's one thing I need to add here, which is a technical condition. Which is that we just call Spade's condition from now on. That this condition holds for GF. So somehow in all these proofs of these inductive conditions, you have to at some point, what I said before, you have to really construct a representation. And without this condition, you don't really know how to actually construct projective representations. And it turns out that this condition actually miraculously holds now for all groups of Lie type except for type D. So this might be a remark. And I think I also talked to Jay at some point, and I think quite miraculous, I would say, right?
Yes.
Actually, this seems to work, always seems to work. So this is really a condition about the stabilizer of your character in the automorphism group, and also there's also some extendability part that you can always extend to this graph field part. You can always extend some representation to the graph field part. And so this is known to hold except for type D. And what will probably happen in the future is that Britta will also prove it for type D, because this is the necessary ingredient to finish really the proof of the, or one of the necessary ingredients to finish the proof of the McKay conjecture. And so you really have a reduction to quasi-isolated blocks. And also, I think, just another remark, what Ellen was saying before, why do we consider not defining characteristic or other simple groups? Actually, we already know that the IAM condition for other groups, so IAM is known for groups not of E type across characteristic. Let's just say to be be a bit on the safe side, let's just assume that is large enough. So, to my knowledge, it holds for the alternating groups for every prime L. There are some sporadic groups missing, I think, and maybe some groups with exceptional Schur multiplier. But essentially, what you should really get from this talk is that it really remains to prove these inductive conditions now for these quasi-isolated blocks. And the good thing is that at least something more is known about quasi-isolated blocks than general blocks. So there's at least, for the semi-simple element S, there's a complete classification by Bonnafé, which tells you in each type what kind of semi-simple elements you have to look at. And usually, this kind of gives you some simplifications if you want to say something about the representation theory. Okay, so I think that's everything I wanted to say today.
Are there any questions for Lucas?
If you're given any finite groups and you know that the IAM conditions hold for all its composition factors,
Yeah.
do you know that it satisfies the conjecture, or is the reduction more complicated than that?
For all composition, I think you need to know more about the not the composition factors, but I think what they call groups involved. So it can happen that you take a normal subgroup and inside there a normal subgroup again. So it's not only composition factors. But actually, so what I haven't said before, or what I haven't said in my talk, is actually if you want to say something here about specific Lie groups, so just say groups of type A, you know that your Levy subgroup would also be of type A. So what you actually only need to do is, if you want to prove it for type A, you only need to do it for quasi-isolated blocks of type A. So somehow you have this only for, in some sense, sub-diagrams of your Dynkin diagram. You only need to verify the condition.
Have you started on the quasi-isolated block?
So, yeah, good question, because I said it had something to do with what I'm doing right now. So it's kind of, the situation becomes particularly nice if you just consider the prime L equal to 2. Because in this case, you don't have too many quasi-isolated blocks. Now this is essentially because if you look at classical types, if you're on type B, C, or D, your center will just be a 2 group. And also, what will happen is that the order of your semi-simple element divides the center apart to some extent, and therefore this can't happen. So in type B, C, and D, you only have actually the unipotent blocks. And also there's a theorem by Caban which tells you it's actually just a principal block. So in type B, C, and D for the prime 2, you just have to worry about the principal block anymore. But that's the nice thing, but the not so nice thing is that actually in type A you have some more quasi-isolated elements. And these are a bit more complicated. So what they kind of look like, still they somehow look like unipotent blocks, but they're somehow, so what you end up with is you have a unipotent block, some group L here, and your blocks will be blocks of some overgroup N, which cover a unipotent block. And you still can say something because this is just a cyclic quotient, but it's still much more difficult because it is not a unipotent block. It has very different features. It becomes more difficult. But yeah, that's yeah.
So is it known that Spat's condition is false for type B, or just
It's just not known. I think
we have to guess?
I would guess that it's correct. Yeah. Surprisingly, I would guess yes, that it was not a type B.
It'll be very annoying if it's wrong. make life very hard indeed.
Yeah. It's also quite surprising because it's even a condition that depends on the choice of your character. So somehow if you take character of SLN for one choice in like the orbit under GLN, for one choice of your character it will be true, but for other choices it will not be true. It's something really that is kind of surprising because it's not, in some sense, canonical, if you know what I mean. It really depends on the choice. And somehow this is also the problem if you want to prove type D, because type D is so complicated, and you have to always, you somehow want to argue, I guess, again, inductively. So you have to make the right choice somewhere locally, and then you have to go up. And you always have to make the right choices, and it becomes a very delicate computation, because there's no reason why certain characters should have this condition. So unless your automorphism proof is abelian, then it actually is satisfied for every character. So when types A and D, it's somehow mysterious why you have these certain characters which have these nice properties.
Are there any more questions? All right, well, if not, then let's thank Lucas again. I believe we're going to Robinson for lunch.
I believe so, yeah. Let's meet at the front door for a course